Okay, Celestine, you were saying?
Okay, so I was able to go through, yeah, what a power amplifier is. I did the question on power amplifiers. Okay, I can say right now I'm comfortable with class A. Sorry. I'm comfortable with class A power amplifiers. I'm still going through B and AB. Yeah. Uh, okay. So today we would have done 4, but we'll do 3 because there's one question that ilinipea shida. So I think we'll start from there. Okay. So okay. So what is a power amplifier? A power amplifier is something that amplifies power. So that is just exactly what it is, something that amplifies power. And then now in this place, I want you to note, you should be able to classify, to look at a diagram and realize that this is class A, this is class B, this is class C. So for today, we'll do class A. So the thing you should note about a class A amplifier is that, I wrote it here. It means that the transistor is operating in the active region at all times. And this implies that the collector current flows for 360 degrees of a cycle. Yeah, okay. So for you to understand power amplifiers generally, you should be able to know how to do AC and DC load lines. So I will not derive this here. I will do it in a question because there's a question worth 15 marks. And you look in a you look for the DC and AC equations and load line equations and so forth. So let me just jump right into the question. So, okay. So there's question 2 here. Sorry for the lighting, guys. I'm in a different place today. I was kicked out. So question 2 says, the power amplifier illustrated below, we have R1 is 33 kilo ohms, R2 is 10, RC is 4.7, and RE is 2.3. RL is 10. So obtain the equations for DC and AC load lines. Sketch the DC and AC load lines giving the values of X and Y intercepts and determine the maximum output compliance. Now, if you see the word output compliance, inamaanisha maximum peak voltage. So it's a term he likes using in exam, but not it just simply means maximum peak to peak voltage. So let's see. Okay, so we have a circuit here. Yeah. So let's start. So, okay, yeah. So the first thing, we've been told to obtain DC and AC load lines. When you're determining your DC load line, you'll have to get your DC equivalent. Also, when you're determining your AC load line, you'll have to get your AC equivalent circuit. So let's start with the DC. Okay, hope it's clear. So DC equivalent circuit, tunasemanga we open circuit. Yeah, places where the capacitors they will behave like open circuits. So here itaenda, so it comes like this. This capacitor will be open circuit, so there's no current here, so this whole part is done away with, and this is an open circuit. So this is our DC equivalent circuit. I think you guys also remember this from first sem. Okay, so let's look for a DC equation. So our DC equation is going to be, so another thing I want you to note is when you're looking for load line. So load line. It's really dark here. Load line, you want to look for VCE, so like output voltage, and output current, so VCE and IC. So those are the two things you want to have in your equation. And then you'll be plotting, okay, so sini y x, so IC itakuwa hapa for DC, for AC inakwanga I capital C, alafu kwa X for DC ni capital V capital CE, kwa AC ni small v capital CE. So that is basically, when you know this, it's going to be so easy for you. So load line, you have to look for VC and IC. So let's start looking for DC. So ukiangalia hapa kwa VC, so let me just hapa na iko hapa, I'll do VCC minus the drop here and the drop here. Okay, and remember IC tunasemanga is approximately equal to IE for beta greater than 1. So that is something that we'll still use even up to here. So my equation will be VCE is equals to VCC, so VCC minus.
Celestine,
Yes.
Celestine, there's a point where you broke just when you're about to start with the whole VCE thing. So would you mind going back, like right when you're starting to analyze the circuit for to derive the DC loading?
To derive VC. So you guys heard what I said here?
Yeah, just after you finished talking about that graph.
Hello? Hello?
Hello? Hello?
Okay, can you hear me?
Yes.
You can hear me now, yeah?
Yes, I can.
Okay, I hope I'm clear. Okay, sawa. So umesema nilikatika wapi?
So ulimalizia kuongelelea hiyo graph.
Okay, so I start here. Sindio, when I'm talking about VCE.
Yes, yeah. Yeah, she's gone again.
So
I think it's there.
for me to get VCE, this will. You okay, Gishiru?
Yeah, go on.
Hello? Okay. So to get VCE, it's going to be VCC minus the voltage drop here and the voltage drop here. And since we're saying IC is approximately equal to IE for greater than 1, IC equal to IC. VCC will be, VCE will be VCC minus, drop hapa ni ICRC minus drop ICRE. So this is what's going on. So the only difference in my equation, it's nothing. I've just said it's going to be us into RC plus. I've just added the resistances. So yeah. Yeah, I think that's okay. Hope you guys are okay. So this is how I end up with this equation over here. So you note, I have VCE, have VCC, I have IC, RC, RE. Another thing to note is, ukiangalia kwa DC analysis, we use capital letters in everything. So you see kama hapa we have capital V, C, E. So DC analysis, I want you to remember that. And I'll show you what we do in AC analysis. So I think this is straightforward. Now remember, we were saying we're plotting IC on the y-axis and we're plotting VCE on the x. Okay? So you can put your equation in the form y is equals to mx plus c. So if I'm able to make IC the subject, this is what I'll end up with. Hope you guys can see. Nimeleta huku VCE, so I have VCC minus VCE. Nikaleta huku IC, then I divided by RC plus RE. Are you guys okay? Someone wave, say yes. I don't know. Cool. Okay.
We're good. Okay, I'm good. Most of
Okay,
us.
cool. So let's put our equation in the form y is equals to mx plus c. So we know our y is IC, our x is VCE. So IC is equals to mx. So VCE ndio x. Okay, let me just see VCC over C plus RE minus VCE over C plus RE. So y is equals to mx. This is our x. So mx plus c. So I hope you guys are okay with that till this point. So knowing this is just enough. So when you're coming to look for, you guys have noted, let me just show you the diagram that we use somewhere here, that okay, that tunakujanga hapa tunasema IC sat na hapa tunakuja tunasema VCE cutoff. So let me tell you why we say that. You remember in last sem when we were saying that ukikuja na VCE, okay, I'm really, my lighting is bad. VCE sat ni 0.2. 0.2, I think, yeah. Yeah. So normally, from what I've seen or from what I've studied, a transistor goes into saturation when VCE is less than 0.3. So when VCE is less than 0.3, your transistor will go into saturation. Now, of course, 0 is less than 0.3, so you'll end up with ISAT. And for you to end up with ISAT, ni kama unatafuta y-intercept. Because if this is y is equals to mx plus c, we know this is our y-intercept. So, ama rather it's where VCE is equals to 0. Nikiweka hapa 0, this whole term goes to 0. So, our IC sat is this, and it is what we're calling the y-intercept. Okay. Mpaka hapo, mmeelewa? Someone give me a yes for me to move on.
Yeah, tumeelewa.
Cool. And then, now the second part is cutoff. When IC is equals to 0, we normally say the transistor is at cutoff. So nikikuja hapa nitafute x-intercept, see I'll make y0. Yeah, if I make y0 and I make VCE the subject of the formula, I'll end up with VCE is equals to VCC. So, and the reason why it's cut off, it's because we are setting IC to 0. And when IC is 0, it means then the transistor is at cutoff. So, hope iko sawa. So yeah, pretty much. If you're able to trace that, you know y-intercept, say itakata kwa graph yetu hapa. I see my graph is not really nice, but your IC here will be your y-intercept ni VCC over RC plus RE. Then your x-intercept is where VCE is equals to VCC. So your DC load line ndio hiyo. So that is what's going on in a nutshell. From this particular equation, because this is our x, gradient will be -1 over rc plus re. So this is why tuliandika hivi kwa class. So are you guys good so far? Because now we're moving on to AC. Hope no one is lost. Because this is actually the basis of power amplifiers. When you're able to do such an analysis, then the rest of them will become very easy for you. Okay. So I hope I'm still being heard.
Yeah,
Sijakatika.
I think we're good. No one has raised any questions in the chat, so
Okay.
doesn't
Cool.
matter.
So now we've done DC, want to do AC. So like I said, when you're doing AC load lines, you have to do the AC analysis. So tunafanya again the same thing we're doing last time. For AC, we normally say to take VCC to ground.
So
And
a
then,
question will come up.
yeah.
Dan is asking what you said about the gradient.
The gradient. So let me write it well here. I've just said, let me look for an extra place to have to use books here. Okay. So we have the formula, or rather the equation, VCC over RC plus RE minus VCE. So if this is our y and this is our x, okay, y is equals to mx plus c. So if x, this is x, which means m ni 1 over, or you can write this term as minus 1 over rc plus re times VCE. Okay, just for this part. Yeah, so this is your gradient, this is your m, this is your x, because this is what you're plotting on the x axis. So cool. So let's move on to AC. So AC, we know we'll bring VCC to ground. Yeah. So tukileta kwa ground, E itakuwa in parallel to this. So we'll have R1, R2 will come to ground. And then capacitors will act like short circuits. So yeah, we'll have a short circuit here, we'll have a short circuit here. But here, the resistor will be shorted out because I think current will definitely pass through a path of low resistance. So because this will just be a wire, it's a short, this one will be shorted out. Okay, so this is what our AC analysis will look like. We'll have R1 and R2 in parallel. We'll have RC and RL in parallel on this other side. And normally, we say RC in parallel with RL is small rc. Yeah, it's just a term to ili usiandike vitu mingi kwa equation yako, but we'll see how we apply it. So in AC, I can say there are 3 equations you need to know. First one, in this loop, there is a KVL here, just looking at this particular section. So here, tunaona voltage kuna VCE plus AC RC. So VCE, okay. Just a minute to confirm something. Oh. What to confirm something? Yeah. So, and you note it's small, like small VCE, like a V. Let me do that. CE plus IC RC is equals to 0 because voltage in a closed loop will give us 0, the sum of voltages. So that's what's going on here. Okay. And then, so this is small c, this is small c, this is small VCE. So this is the first equation you have to know. the second thing you have to know is that the total IC will be the IC due to the AC collector current component plus the DC collector current component. So this is the second equation. The third equation you'll have to know is that small v capital CE is equals to small VCE plus VCEQ. So this is the AC component, DC component. So this is the third. When you know these three, then you're okay. So using the three equations we have, okay, so let's see. We can use equation 1 and 2. Here we can make IC the subject because we have small IC here and small IC here. So IC will be equal to minus small VCE. So I hope you guys can see that over RC. And then this is what we'll substitute in here. So we'll have I capital C is equals to, is equals to minus V CE over RC plus ICQ. So I hope that's okay. And then from here, I know my expression for this. No, wait, I should make this the subject. So I'll come and do small VCE is equals to, should be small VCE minus big VCEQ. Yeah. So this is what I will substitute in here. So I'll end up with minus VCE minus VCEQ over RC plus ICQ. So we have that. So yeah. So this is, remember, this is capital C. This is capital C. Yeah. This is small c. So we end up with minus VCE over RC plus VCEQ over RC plus ICQ. So this is our AC load line equation. This is what's going to help us plot. And again, like I said, we're going to be plotting IC against VCE. So IC is our Y. VCE, you remember this is the AC component. The capital one, yenye iko capital kila kitu ni DC. But AC component, you realize the first letter is small and the preceding ones are capital. So this is our X. Okay. So if this is Y is equals to MX plus C, it means our Y intercept itakuwa IC is equals to this part. VCE, this is a VCE Q over RC plus ICQ. And then our x-intercept ni penye IC ni 0. So again, if this is 0, then it means that inakujanga VCE is equals to should be ICQ RC plus VCEQ over RC. Okay, so any questions still there? Anyone who's not understood anything that I've done? At any point? Are we together? Mnanisikia?
Tunakusikia, we are together.
Yeah.
Celeste.
Yes.
That
Yeah.
VCE cutoff for AC, uh,
VCE cut for just
the last equation is done.
yeah.
It's over RC.
This
It's not over RC.
oh, it's supposed to be time. Oh, it's not supposed to be. Ah, true. Sorry for that. Sorry. The circled point, Aburudia, please. Hapa. Okay. So what's going on here is I'm putting my equation in the form of y is equals to mx plus c. Yeah, okay, cool. So if this is what I'm plotting on the y, VCE is what I'm plotting on the x. Then inamaanisha kama niko na equation y is equals to mx, then my m ni itakuwa negative 1 over rc plus c. So the remaining part of the equation, as long as it's not part of mx, it is y-intercept ama c. Do you understand there, Mike? Mike? Hello? Haya. Mnanisikia?
Tunakusikia.
Tunakusikia.
You gathered everything. Okay, I don't know what the
Oh,
question means, but okay.
okay. Sawa. Yeah. So, if you have your this is cut off, yeah? And remember I said it's cut off because ICs, we're setting IC to 0 to get the x-intercept. And when we set the y, no. Yeah, if we set the mx, if we're getting the y-intercept, we're setting the x to 0. So we know that I, capital C, will be VCEQ C plus ICQ. So when you're plotting your graph, have AC versus DC. Of course, down here we have AC, VCE, VC capital E. Don't forget this. Capital V, CE, Q. That's what they call it. So your y-intercept hapa kwa IC utakuwa na VCEQ over RC plus ICQ. And then your x-intercept itakuwa VCE yako is equals to, okay, let me say VCE, small VCE is equals to ICQ RC plus VCEQ. So this is how your AC load line will look like. And normally you'll realize your AC load line has a steeper gradient than your DC load line. Yeah. So if this is AC, then your DC will probably look like that. So yeah, I think, yeah, that covers the question. Was saying obtain equations for DC and AC, sketch DC and AC load lines, giving values of x and y intercept. So hiyo tumefanya vizuri. So what compliant? It maximum peak to peak voltage. So this one is pretty straightforward. So, okay, before we go there, hatujatafuta the actual values of x and y intercept. So let's do that. So you realize for the DC analysis, okay, I didn't finalize here, but for DC analysis, hapa kwa y intercept itakuwa VCC. Our VCC was, I think, 30 for the question we were given. Let's see it. Yeah, anyway, you'll be given value of VCC, we were given RC, we were given RE. So if, for example, our VCC was 30, utakunja tu sasa you substitute your values. So from here, RC is 4.7K plus RE is 2.3K. So your answer will be the result of this. VCC is equals to VCE. So that's your x-intercept. If your VCC was 30, your VCE is 30. Now, you have to find ICQ. You have to find VCEQ.
Hey, hi Celestine, could you kindly back up by about 10 seconds?
Can I do what?
For about 7 seconds up, or the feed went numb. So by about 10 seconds.
My feet went numb. Oh, where? Where was I? Were you
Just
guys
when ulikuwa na move ku brush up on something to do with DC, just when ulikuwa na brush up.
When I was brushing up.
It's okay. I thought I missed something there. It's okay.
When I was substituting the values?
Okay. Okay. Seems like I'm not
Guys
far.
can't.
I'm not far gone. It's okay.
Okay. I hope you guys are cool. Usikuwe umenyamaza na sisikiki. Okay. Sawa. So let's now do for AC analysis. Let's find our actual, like the value of the y-intercept and the value of x. So we see y q.
Celestine, hello. Celestine.
Okay, well, that is unfortunate. Celestine left us. So what do we do now?
Patience is a virtue, I guess.
Let's give her a few.
Sorry?
Let's give her a few.
Yeah, mtu asimpigie just in case kwanza anajaribu ku get back. Let's just give her like a minute so that she sets up. I don't know. Namerudi, eh? Yeah, she's back. Okay.
Welcome back, Celeste.
Sorry, that guy. Today I'm in the place that has the worst internet. So, poleni yake guy, I hope amjapotea sana. Aya. So to get VBE, to get VB, we're going to use voltage divider theory. So voltage divider theory says that the resistor near the ground, okay, so R2 over R1 plus R2 times VCC. Our VCC was 15, actually it wasn't 30. So R2 over R1 plus R2 times VCC is 15. So you'll be able to get your VB. If we have VB, tunaweza pata VE because we know VBE is equals to VB minus VE. So to get VE, I know I'll have VB minus VBE. So VB yetu tumeipata as 3.5 minus VBE of course is 0.7 to get our VA as 2.8 volts. If we have VE, we can get IE because our VE is here. It's 2.8 volts. So to get IE, definitely it's just going to be 2.8 minus 0 over RE was 2.3. Yeah. Yep. And because we are assuming beta is greater than 1, then this is also equal to IC. So if you do that, you'll get your IE as 1.22 milliamps. I think that's okay. To get VCEQ is VC minus VE. So to get VC, let me just go back here. So VC is VCC minus drop here IC RC. So that is basically what we did. So I said 15 minus IC is equals to IE. So remember that this is rather ICQ or IC. So 1.22, 4.7K for me to get, yeah, 15 minus that. So my VC is 0.28. I have VC, I have VE, I can get VCEQ. So VCEQ is VC 9.28 minus VE 2.8 to get my VCEQ as this. So yeah. So let's look at our equation. Tumepata ICQ, tumepata VCQ. Let's look for RC. RC is simple. We said RC from AC analysis is this resistor in parallel with RL. So yeah, basically you plug in values. So you'll come and say 4.7 in parallel with 10K. Okay. Yeah. Yeah, for you to get your value of RC is 3.2. So kishapata hivyo, you come now in proxy. So you say we were told to find values of X and Y intercept. So in Y intercept, we got our IC as this, our VCE as this, and RC as this. You just simply substitute and find the answer. Same here, we already have value of IC, VCEQ, RC, VCE, no, sorry, VCQ and RC, sorry for that. It was this, 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 and this. Mike is saying 15 to 5. 15. Hey Mike, what does that mean? Something in Ethercom. Hello? Can you guys hear me?
Yes.
Sorry? Oh, okay. Okay. Mike, I'm not really getting your question. 15 minus 5. Yeah. 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 Okay. But let me just confirm. I don't have my calc here. Sorry. But okay, you guys will check when you're redoing the question if what Mike is raising. I'm seeing 0.0 up or something. No, this is 9.28. 9.28. Yeah, I hope you guys are good until there, because I'm done with that question. That's 15 marks. We're done with. How did I get ICQ? I got ICQ normally the way we get IC. Remember the way we said VCE? No, IC is going to be VE minus 0 over 2.3. This is my IC, and it's equal to my ICQ. Rather, my operating current, collector current. I hope you're good, Daniel. Yeah, I hope you guys are good with question 1, because I started with that because I felt like it was a basic for how amplifiers are going to work. What actually, this is what you're going to do in your class B, class AB. So sahi ukiiva hii, next time it will be easy for you to understand class B and AB. Okay, so where was I? So let me move on to the next question. Question 2. Yeah, so I think this one is going to be pretty much straightforward, but it has a little more math to it, so let's do it. Okay. For Class A amplifier illustrated below. Determine the values of ICQ, VCEQ, and AC load resistance RC. So if you see anything inasema ICQ, VCEQ, ujue Q just means the operating point, the operating current, the operating voltage. So that is what you need to remember. Now, the question I've just done, I don't know whether I'll call it I won't say it's an AC amplifier per se, it's just a power amplifier, it's a general. But now we're narrowing down to AC amplifiers right now. So there's a place here I was saying sorry guys. An amplifier that is biased in the active region is an class A amplifier as long as the output is not clipped. So as long as output is not clipped, it is biased in the active region, it's an AC amplifier. So for it not to be clipped, we will realize current will flow throughout the cycle. There's something we did here, and you'll note for active region, there was a place we said the operating point, or rather Q, is located in the middle of the load line for class A. So I want you guys to remember that. I want you guys to really remember that. Something I'm looking for here. Yeah, this is it. So I'm not saying this is okay. Let me just use this as an example, because the operating point, the Q, is at the center of the AC load line. So you notice this is how an AC amplifier, let me say, load line will look like. Operating point Q, itakuwa hapa, and there will not be any clipping. Yeah, there is maximum swing on both sides. That's why tunasema IC flows for 360 degrees for the AC cycle. So remember that for class A amplifiers. Okay. Tuko sawa hadi hapo? Because we want to do this question as fast as we can, because you already have a basis. Okay, I hope you guys are still hearing me.
Yeah, we can hear you.
Cool. Thank you. So for the class A amplifier illustrated below, determine the values of ICQ, VCEQ, AC load line resistance, RC. Kiona hivi, this is free marks, because it's basically what we did last sem. So ICQ, you're just looking for the operating point. It is biased in the active region. Yeah. So the operating point ICQ ni kama unatafuta IC na VCE. Only this one has values already. So let's do this one. Also remember, when you're seeing it in capital, inamaanisha this is DC analysis. Okay. So if this is DC analysis, remember to always find the DC equivalent circuit for the circuit you've been given. Again, for DC equivalent circuit, capacitors act as open circuits. So if this is an open circuit, hiyo itapotea, and hii itapotea. So let's see how we'll find ICQ and VCEQ. So VB will use voltage divider bias. The resistor near the ground, connected to the ground, over the sum times VCC. So we'll have 68 ohms over 68 plus 490, these two, times VCC, which is 30. Okay. So I hope that's okay. That is just voltage divider. We're able to find VB. Once you're able to find VB, you're very sorted, because now you just find VE. Now, if you know VBE is VB minus VE, then you'll know VE is VB minus VBE. So we found our VB is 3.7 from our calculation, minus 0.7 for us to get VE is 3. Okay. So VE, go up. Use a pencil. Can't see my pencil. So VE iko hapa. Tumepata ni 3. So to get IE, it's going to be VE minus 0 over 200 ohms. So that is what I did here. So VE minus 0, 3 minus 0 is just 3 over 200. To get my IE is 0.15 amperes. But for beta greater than 1, then IE is equals to IC. And the IC you're getting here is your operating. Hiyo ndo maana tunaongeza hii Q. It's the IC where your transistor is operating. So it's it's something that, yeah, that's where it comes from. So tumeshatafuta ICQ. We were told to also look for VCEQ. So this one is pretty easy because we know VCEQ is VC minus VE. So VC is VCC. So first you find VC because VE tulishapata hapa ni 3. Copy VE. So this is okay. So you find VCEQ. VCEQ, no, you find VC, sorry. You find VC, sorry. So VC is supposed to be here. VC is VCC minus the drop here. So 30 minus IC times 120. So 30 tulipata IC as 0.15 times. So you find your VC is 30 minus 18 to get 12. You have VC, you have VE. So you have 12 minus 3 and your VCEQ is 9. Okay. So I hope, are you guys okay up to there? Someone give me a yes. Okay, cool. Yeah. So 3 marks. So we found that, and find AC load resistance RC. This is really easy because when you're doing your AC analysis, now when they say AC load resistance, make sure you have an AC equivalent circuit in your mind or you've drawn it somewhere. And if you're able to remember, I can't find my pen. If you're able to remember, hey. Hello? Okay. If you're able to remember, we were saying that kwa AC, do I have to draw this circuit? Okay, I'll just do the AC equivalent. So this one will go to ground because it's attached to VCC. So VCC goes to ground. So tuko na R1 in parallel with R2. And then we also have, now AC, this one will be shorted out. So your emitter will go to ground. So your emitter will go to ground. Yeah, this one will come to ground. This is a short. So we'll have RC in parallel with. So RC in parallel with RL. And these two in parallel detonator RC. So RC is going to be RC. So when they're asking about AC load resistance RC, they simply mean this RC in parallel with RL. So you can, it depends. If you are genius, sharp, you don't have to do it. You just picture it. But if you feel confused, you can just draw it. Kuna pressure. So our RL was 180, our RC is 120. So we do times plus for you to get your AC load at 72. Hebu niambieni hiyo si free max ni wase.
Yes,
Okay.
free max.
Aya, anyone has any question? Hiyo si free max.
Umesema tuseme.
Okay. Aya, sawa. Basi, I'm just saying it's something if it comes, you can easily get it, like all of it, ICQ, VCQ, and RC. So the second part says plot the, this was supposed to be, is it AC? So it was supposed to be DC. Plot the DC load lines. Okay. So yeah, we'll use what we've used in the previous equation, but now we'll use actual values. So for DC, you guys remember, VCE is VCC minus IC RC plus RE. Do not forget this RE. Do not forget it. Because what is going on, you want to find VCE. We have VC here, VC here, we have VE here. So if I do VCC minus the drop here and the drop here, I'll be getting VCE. So don't forget to put both these resistance into account. And again, the reason why you're using IC on both is because we're assuming IE is equal to IC. So that is where we are coming up with this equation from. So yeah, I think this is what we've just done, because we've made this the subject, because it's in the Y. We have our X here, IC, VCQ is X. So we're supposed to plot the DC load line. So at VCEQ is equals to 0, yeah, we'll get the Y-intercept, and it is VCC over RC over RE. So to get IC, VCC ni 30, RC was 120, RE was 20, we're given in the question. To get your IC sat is 0.214. Again, when you set VCE to 0, the transistor goes into saturation, because when the voltage is below 0.3, yeah, it makes the transistor go into saturation. So that's okay. This is what you'll plot on your Y-axis. At cutoff, now when you're getting your X-intercept, we are making Y 0. And if we make IC 0, the transistor will go into cutoff. So at cutoff, when this is 0, VCEQ is equals to VCC. So you'll plot VCC on your X-axis, and your VCC was 30. So with that, you're sorted, because you'll come to your graph. Let me just do a small sketch here. You have your IC. Your IC copy. IC was 0, yeah, 0.214. The VCE is 30, yeah, and that's your DC load line. Yeah, you just come and say VCEQ is equals to VCC, yeah, and you're done. So that is how you'd get your DC load line. Find the maximum output compliance. Again, output compliance is maximum peak-to-peak voltage. It's just a fancy word for peak-to-peak voltage. So maximum peak-to-peak voltage, hiyo juu unaingia kwa AC sasa. Okay? Because it's AC. Yeah. So again, you look for your, I hope you guys remember the 3 equations, and then the substitutions we made to end up with this particular equation. Okay, this is our AC equation. Yep, this is our AC equation. Ooh, sorry. So at saturation, tukitaka kutafuta Y-intercept, you could always label if you want it to go easier. Don't label the wrong VCEQ, because here AC inafaa kuwa small v, capital CE, and DC ni capital V. Just make sure you're able to remember that. So to get the Y-intercept, we set VCE to 0, IC sat. It should be IC sat. So IC sat, tutabaki na ICQ plus VCEQ over RC. So you could, yeah. And then at cutoff, we have before we do that, at cutoff tunasema x IC is going to 0. So it's like we're looking for the x-intercept. So when that happens, we normally find our small v. The AC component is equals to ICQ-RC plus VCEQ. So we calculated ICQ. Yeah. Just so you guys remember, we have ICQ here. We have small RC here. So this is what you're substituting here and here. Not so clear. Okay. Plus VCEQ is 9. Yeah. For you to get that. There's something I have to confirm here. Yeah. There was a note the lecturer made in class. He said that the maximum peak voltage can either be VCEQ or ICQ RC, whichever is smaller. So the first thing you're supposed to do is to look for VCEQ. VCEQ is 9. Sindio? And then IC, actually not, you don't even have to do this. Yeah. IC QRC is 10.8. So 9 and 10.8. Between this, maximum peak voltage, okay, not maximum peak to peak, maximum peak voltage is going to be the smaller, so we'll take 9. So if our maximum peak voltage is 9, our maximum peak to peak voltage, okay, is going to be, should be maximum peak 2 times 9 to get 18. Yeah. Who has a question till there? Yeah, mko sawa? Someone give me a yes. Hello, Yulo.
Yes.
Hello.
Oh, okay. Okay, cool. So yeah, that question is done. So yeah.
Mike asked to do the last line. I think he's
Mike,
referring to the point which we are talking about, much smaller.
so you're saying I go back here.
Yeah.
Maximum. Sorry. So maximum peak voltage is either VCEQ or ICQ times RC, whichever is smaller. So what is this question? Actually, here, because we'd already gotten did we get VCEQ? I think we got it. Yeah, we got our VCEQ as 9. Yeah. So you either look at VCEQ, which was 9 volts, or ICQ, small rc. So remember, this is small rc. I just, you don't have to write this in exam. I just did it so that you guys know that you have to use small rc. Yeah, we got ICQ as 0.15 and small rc as 72. So 0.15 times 72, I'm getting my answer as 10.8 volts. Now, my maximum peak voltage, okay, maximum peak voltage will be either VCEQ or ICRQ, one of them, but yenye ni ndogo. So, because this is smaller, this will be my maximum peak voltage, and this will be 9. Maximum peak to peak voltage will be 2 times maximum peak. So itakuwa 9 times 2, which is 18 volts. Aya. Mike, are we good? Cool. So there's one more question. I was going to do a question on transformer, but nilikuwa na nilijipata kwa shida. So I don't want to do a question that I'm not sure about. So there's one question at least that I'm sure about. Let me just do it now. It was in our notes, but I saw it in another cut. So if you're able to do this and you see it in a past paper, I think you'll be able to do it because, yeah. And he didn't finish the whole question in class. And I thought this was a good question because you're able to learn new points. Because we're now going to talk about efficiency and we're going to talk about power gain. So I think this is going to be a really good question for us. Okay, kidogo. Okay. So again, we have a class A amplifier. This is how a class A amplifier looks like. It pretty much looks like what we had most of the time last sem. Yeah. Given the input resistance at the base is given by 1 kilo ohm. Okay. Obtain the power gain. Just a moment, that is not the full question. The full question says, for the class A amplifier illustrated below, the input resistance at the base, Rn base, is 1 kilo ohm. If the output voltage, peak to peak, is 18 volts, determine the power gain, power dissipation at the transistor, and efficiency, taking into what was that? Into, I think, account power dissipation in the biasing resistances R1 and R2. Okay. So now, first, you'll have to look at AC equivalent. The reason why we're looking at AC equivalent is because now we want to do power gain, and that is from the point where nakujana, we need to obtain AC equivalent circuit for us to be able to get AC power input and AC power output. Something I want you guys to remember is power gain is not efficiency. Power gain is power out over power in. Just the same way voltage gain is voltage out over voltage in. And the same way beta or current gain is current out over current in. So that is just power gain. So we're going to use AC analysis for this power gain thing. Efficiency is a whole other thing. It's power output from in AC over power input in DC. But let's look at power gain first. So power gain is power output over power input. Note that power out is yes, Fiona, yes, absolutely. So when it comes to AC, when we're doing power, you have to use RMS values. Okay, so yeah, remember even in ECT tukifanya second year, the way anaitwaje Mr. Professor Uma used to say AC power is V RMS times IRMS. So that is what we're going to use. So yeah, this is the second note. Make sure you use RMS values in AC. Okay. So we need to obtain input and output power. To do this, we first draw equivalent AC circuit. So I hope you guys are able to follow, because we know in AC, capacitors are short circuit, so this will short out. Short out. And then this will go to ground. So VCC goes to ground. So you'll have R2 in parallel with R1. Ndio maana tuko na R1 na R2 hapa. And then, yeah, this is R pi. R pi, in the question we've been told, we have Rn base, yeah, resistance at the base. So in the resistance, looking at the base, tulikuwa tunaita R pi. If you remember, I think we're doing H parameters last time, yeah. So we've been told in the question, yeah, that there is an input resistance looking into the base, which is that. And then we have 120. Of course, when this goes to ground, 120 itashuka ikuje kwa ground ikue. Okay, yeah. Ikue in parallel with the rail. Remember, this is shorted. So we'll have 120 and our 180 here. And this is RC. Yeah, this is small RC. So let's see. So kuna power in. So let's first do power in. It's going to be V in RMS, sorry, over root 2 over 3. So we know, okay, no, power is V squared over R. Yeah, so this is basically what's going on. But now he V to make in terms of RMS. I should not have put this one here because it's redundant. So this is redundant. Having root 2 there already makes it RMS. So V in, now in the question we're being told that where is this? Oh my god. I hope sijakatika.
You're
Hello?
still there.
Can you guys hear me?
Yeah, you're still here. Well, for me, your picture is
Hello?
so.
Oh, okay. Hello.
Yeah, Celestine, we can hear you.
Cheryl, can you hear me?
Celestine?
Hello?
Can you hear us?
Okay. Now, okay. Can you guys hear me?
Yeah, Celestine, we can get you.
Andrew?
I don't think she can hear us.
Oh, she isn't. Mtu amtext.
Aya, mnanisikia?
We ndio utusikie. Wacha uoga. Sasa hiyo nitamwambiaje? Sasa wewe. Okay. All right, let me text her. Guys, please, when you another type fast enough. Okay.
Well,
Right.
she has a code.
I should have. Okay, right. Another minute. Okay, so Fiona, what's this thing about? Note that power out is AC. Oh, yeah. And power in is DC. True. Wait, but is power in entirely DC? Oh, yeah. Because the whole idea is the AC power in is probably minimal. Okay. Oh, she's back. Mic is off.
Sorry. Do you guys have any questions?
Kwani umemaliza?
No. I'm still going on. I hope to come. Sorry. So tomorrow is V squared over R. So in the input side, yeah, we're looking in the input side. We're seeing our Rin is 490 in parallel with 68 in parallel with this 1 kilo ohm here Rin base. So yeah. So I hope you guys, so this is how I did for 90 in parallel with 68 with that to get this. And then our V in, we're being told our V in is 200 volts peak to peak. But I've noted we're only using peak voltage. We're not using peak to peak. So atakuja aseme 200 inafaa kwa millivolts. 200 millivolts, just say millivolts divide by 2 is 100 millivolts. If you convert 100 divided by 1000, you get 0.1 squared over root 2 for the voltage, and then times Rin. Okay, times 1 over Rin. So 56.3. I hope you guys are okay till there. To get your power in, as 0.09 milliwatts. We'll do the same thing on the output. Now on the output, we're looking on the output side. The resistance we are seeing from the output side, yeah, is going to be 120 and 120 in parallel. For me to get my RC is 72. And then my V out, remember, ni 8 volts peak to peak, but we're going to use peak. So 18 divided by 2 is going to be 9. So 9 squared over root 2, yeah, times 1 over 72, because this is our route for you to get this. So power gain is power
Celestine, I
output.
have a question before you go. I have a question. Concerning when you're evaluating for the output power, it's V squared over R, right? V RMS squared over R. As
It should be, yeah.
yeah. Now for the R out part, get it? Do you use the effective AC output collector resistance, or
Distance.
do you resistance impedance?
Resistance.
Resistance, yes, resistance, or do you use the load resistance?
No. You'll use
The load resistance.
this RC, which is the load in parallel with RC. This was RC, and this is RL. Yeah. Because
Why?
the resistance you're going to be seeing looking on the output side. Yeah.
That's
Got,
the only.
oh yeah. Okay. Sorry. Yeah, that's okay. Sorry.
That's it.
Yeah. What do you mean that's it? Because
From various texts, reference texts that I Malvino and Cedric Smith, they said that when you're calculating the output power, you use the power that is being delivered. The V out is being measured across the load resistance. So you evaluate for the power that's being delivered to the load. The load being RL only, not the parallel combination of RC and RL.
okay. Wait. Give me a moment.
Kamuta used RC. That's what you're checking.
Sorry.
I know.
Yes, he did use
Dr.
RC. It's just something. AC load resistance, RC. So your question is, you want power to be measured only across the load, not across.
I was asking why, as in from the research you've done, and to evaluate all the questions, we consider more accurate between measuring across RL only, measuring across small RC.
Okay. I wouldn't say I did research because for me, what I was looking at when looking at R out, yeah, it's the resistance I'm seeing on the output side of the transistor. You see, what do I see when I place my eye on the output side? I know if anyone else has a more decent explanation to that, to what Gisho is asking.
Another question that may, I don't know if it's going to help or make matters worse.
Okay. Celeste,
Yes.
like when you see what Kamucha is doing, even in his notes, like even this whole this work is typed out for us for notes. It's when you're going through his work and you go through Malvino's work, they're almost similar. Even the examples and they're they're very similar. Everything, like even the text, someone can be twisted. So, but then there comes a problem where he starts the power output Malvino uses, the AC power output Malvino uses. I don't know if some of you have those books, but that book, but he keeps saying it's that RMS, that V marks RMS divided by RL, not Z out, because it's power delivered to the load. And also Sejong also CRL. So I don't know. It's been something which has gonna it's very confusing because now the example even which is being used in Malvino, it's the same example even the one which Kamucha is using, but then now it starts to deviate when you come to power output, even the answers and the efficiency, everything just starts being different from that. So I don't know if now the question is
What
why
yeah. Why are we not using RL? Yeah.
why did
And
Kamucha
not
decide not to use Z out instead of RL? Or was it a mistake on his side? Or I don't know. Yeah.
I can't think it's a mistake because I discussed with someone from the previous year. Yeah. So okay. For now, because you don't have a solid answer to this, you can ask Kamucha on the Google classroom. Bill, you can ask him on our behalf. Yeah, Bill. So that we're able to work out how we'll work with this for at least that part. And then please send the reference text you're using. I don't think I've seen it. I've been struggling, man. And you guys have reference text. Hello?
We get you.
Yeah.
You
We do.
guys hear me?
Yeah.
Yeah, we get you.
The text would be the reference text Totuma
Mtatuma?
for group,
Telegram,
yeah,
WhatsApp, anyway. Sawa.
Telegram.
Okay, cool.
I think the audio book segment we've already sent to the Telegram group earlier. Julia, yeah, Marvin, yeah, Totuma.
Okay. Okay. Sawa. So, okay, let's put a star on that. Okay. But just power gain is power out over power in. So I've seen there's an issue on power out. We'll ask the lecturer that one. Transistor power dissipation. There's one question I had for anyone who can answer though. Okay, yeah. Transistor power dissipation was simply VCEQ. Okay, from here. VCEQ, ICEQ, ICQ. So we're being told when no signal drives the amplifier. That is, the quiescent power dissipation is given by VCEQ, ICQ. What do they mean by no signal? Do they mean there is no AC signal that has been fed into the amplifier? What do they mean? Anyone who has an idea what that means? Hello? Just like I'm seeing your microphone on.
Yeah.
Okay, Fiona. I'm asking.
Mhm.
We're being told when no signal.
Could
We're being told
could
no.
what, what's the
Sorry.
page? What's the page?
This is page 18. When no signal drives the amplifier, the quiescent power dissipation is VCE times ICQ. Does it mean when there's no AC signal that has been fed into the circuit. I don't know. What does that mean? What is that data?
Wait. It says when no signal drives the amplifier, that basically means that of course, it has the DC. In order for it to even be called the amplifier, that it has to be biased, it has to be powered up, it has to have VCC or VEE, whichever formation you want. So that means he's talking about the AC. He's talking about there is no AC, there is no small signal being sent to as input. So if that happens, the quiescent power dissipation is you take
That.
the VCEQ, ICEQ. Okay, makes sense.
Yeah, because that is what I used. I used DC analysis for to get my transistor power dissipation. Yeah. So of course, when you're doing this analysis, you have to get the equivalent circuit. So first you'll find VCEQ. You find a CEQ, then you get VCEQ. So you normally start from VB. So it's basically what we've done in the previous question. So VB is going to be 68 over 68 times 490. No, 68 plus 490 times 60 times 30. So our VB is 3.7. Get our VE as 3. If you have VE, we can get IE. So if you have VE, so IE is going to be VE minus 0 over 20. So that will be 3 over 20 here. Get 0.15 amperes. VCEQ. So you already have ICQ, so let's get VCEQ. C minus E. Let's get VE, VCC minus ICQ. IC is 30, is 0.15, IC is 120. So I'm getting that from here. VC for our no, so 30 minus the dot here. 52 and 120. So yeah, thank you guys. It's just the same thing. You need to get your VC is 12, your VCQ is 12 minus VC minus that. So you have the CQ. VCQ, we have ICEQ. So 9 times 0.15, you get 1.55. So this is our power dissipation thing. Yeah. Okay. I hope mko sawa hadi hapo.
Hello, Celeste.
Yes. Yes.
Celeste, let me interrupt kiasi. Hapo kwa R-in.
R-in. Okay. Yeah.
Yeah. Ini sipati 56 ohms. I don't know. Can you just direct me on how you got 56 ohms?
I got 56. We have 490. So 1 over 490 plus the 68. So 1 over 68 plus there is 1 kilo ohm. So 1 over 1000. Then 1 divide by to get 56.3. So this one, remember, it's only for 2 resistors. Yeah? It's only for 2 resistors that you can do the product sum thing. 120 times 120 over 120 plus 124. But for more than 2 resistors, you have to do ile the long, ile high school too. 1 over 490 plus 1 over 68 plus 1. And then you do the reciprocal. Okay. So I hope you're okay, Situne. Yeah, so let's moving on swiftly, as Joseph says. Okay. So efficiency. Now we want to look for efficiency. Now remember when I was saying the efficiency is now going to be AC power output over DC power input. So to get DC power input, of course, it's normally VCC plus ICC times ICC. Sorry. So ICC is ICQ I1. Let me show you what that is. We're going to have ICQ equal upper. Then we're going to have I1 equal upper. I1. So ICQ I1. I1, there's a particular formula you use to get it. It's very easy. Pretty straightforward. It's VCC over the sum of this. It's just the way you normally see current is voltage over resistance. So we're saying ICC, current inaingia hapa, what I'm calling ICC, is equals to I1 plus ICQ. So let me just label that here. ICC is I1 plus ICQ. So I have to look for I1, I have to look for ICQ. So let's start with I1. I1, I've told you there's a formula. So you have to remember this. It's VCC over R1 plus R2. Okay. For me to get that. Then I have, I think I was able to get ICQ here from our previous question. Yeah. Roman 2. So I have 0.15, which is our ICQ, plus I1, which is 0.05. So this is ICC. So yeah. So your DC is going to be VCC, which is 30 times ICC, 0.24, to get 6.12 watts. Now for AC tumesema bado mko na shida. You guys have a problem with power output because this is the output I used for the AC output I used. So AC output is 0.56 over 0.56 over 6.12, which is our DC input. To get times 100 to get our efficiency is 9.15%. I'm done with the last question. Any questions in this particular question that I've just finished? Any questions so far? Put your Z out, please explain. Put your Z out. Okay, so if at your Z out lean, the way I had done it, but people have raised issues about it. So, but the way I had done it is, we normally say, okay. So if we make the draw the AC equivalent for this circuit, VCC will go to ground. Yeah. So tutakuwa na RC in parallel with RL. So ndio hii RC yangu na iko in parallel with RL. And the parallel combination of these things ndio nimetumia as my AC output. And that is what I used for my R out. So yeah. Or my Z out, output impedance. But there is a question here that people have raised, and we are hoping to ask the lecturer within the course of tomorrow. I hope you're okay, Lynn. Yeah, I think we're pretty much done with everything. I was not able to go through class B vizuri. Oh, there's a question on class A, transformers. It's a 5 question. It's a 5-mark question. Yeah, I experienced an issue in calculating maximum efficiency. Maybe you guys will help me. I'll take a picture and send to the group. Hii tumefanya. See, tumefanya. Obtain the... My camera is not good. The power amplifier illustrated. Obtain the expressions for DC and AC load lines. Sketch the DC. XY intercepts. Determine the maximum output compliance. We're good. So if this question comes, it's 15 marks. Yeah, this question. It's pretty much the same thing we've done. Kuna hii transformer. It's pretty easy, but nimeshindwa na the last part. So I'll send it to the group for you guys to try. It's only 5 marks. Yeah. So this is a typical question. Question 1, you're being told to define gain, input resistance to derive, I think. Yeah. 10 marks. This is another 10 marks. So ukikuwa umeivisha easy topics, you can easily score the whole of question 1 and 2. Yeah. Now question 3 hata uokolea another, 15 or 10 and you're good. Okay. And I'm so sorry, Lynn. Aki nilikuwa nafaa kukutumia maswali. I am sorry. I'm going to send the questions to the group. If you guys have no questions, I think I'll stop there. I don't know when we'll meet next, so I'll leave Gisheru to take over from here. Gisheru?
Okay. Thank you, Celestine. Thanks a lot for taking us through most of class amplifiers. Before I go any further, is anyone who feels well versed in transformer coupled class A amplifiers? Maybe you can take over for Celestine. Because personally, I feel like I'm missing, but I won't be able to explain very well, and I don't want to do that. So if there's anyone who feels like wameshika hiyo concept ya transformer coupled,
Okay. Yeah. Nani? Someone is talking.
No, it's just you.
Transformer coupled was okay because the question we did in class is, let me say, it's actually the same. It's actually similar to this question that is here, the one for 5 marks. It's pretty straightforward. But now we did power, maximum power output. I had an issue with efficiency because I was not sure how to do the input side. Okay.
Okay. You can just go through that then.
Let me through what I already know. Yeah, I've not. Yeah, let me just go through whatever I already. So the reason why kwanza we have a transformer coupled AC amplifier was because the efficiency, okay, we've done class A amplifiers and we found the efficiency is about 25% or less. So that is very poor efficiency. And to improve the efficiency, we're being told a transformer coupled class A amplifier is employed. So to improve efficiency, this is how they came up with transformer coupled class A amplifier. That uses a transformer to couple the output signal from the amplifier to the load. So this is very easy because you guys have done transformers. Okay, we have done transformers in electrical machines, and we know this. We actually know these equations because we know N1 over N2, V1 over V2, I2. Of course, current in interchange. So yeah, knowing that power in is equals to power out. So here we have just a moment. I1 on the primary side, yeah, I1 squared Z1 on the primary side is equals to I2 squared times Z2 on the secondary side, but Z2 is our load, RL, yeah. Hapo ukiangalia Z2 ni load. So yeah, so I'm going to use nini. So normally we get Z1 is I2 squared over I1 squared times RL. So for example, in this equation, if I'm going to get Z1, then I'll have, okay, so actually I hope I'll be clear. So I have RL, it's not so clear, but I'll send it to the group. I have RL is 4 ohms, VCC is 515, ratio of N1 to N2 is 7/2. Determine the maximum efficiency of the amplifier for zero signal collector current of 100 milliamperes. So before we move on, we know I2 over I1 is the same as saying N1 over N2. Okay, they are both squared, so I'll just say squared times RL. In the question, we have been given the ratio of N1 to N2 is 7/2. So 7/2 squared times RL is 4. So this is how you'd get your Z1 on the secondary side. Yeah, let me just 49 divided by, it should be 49. Determine the maximum efficiency. So in the maximum power output, we're saying P max is I squared max RMS Z1. No, okay. Yeah, we remember in efficiency, it's power out in AC over power in DC times 100. So power out, of course, when you're using AC again, we use RMS values. So I note is basically what you're given. Hapa unaambiwa zero signal collector current of 100. So that's your I note. So we are saying that P out max is I naught squared RMS, of course max, times Z1. I don't know why they're using Z1, but yeah, just,
The
oh yeah,
last
I get why they're using Z1. I get it and I don't get it, I'm not so sure. But yeah,
last thing.
yes.
I have a question. What exactly do they mean when they say zero signal collector current?
That is the same question I asked, and they said it means we. Oh wait. Yeah, that was something else I wanted to ask actually. Yeah.
Okay, can anyone explain what they mean
Yeah.
by zero signal
I
collector
think that's
current?
one of the things that was ilikuwa inanisumbua kwa hii swali.
Isn't zero signal collector current equal to ICQ? Like I capital and subscript
Oh,
CQ capital.
DC complement.
Yeah.
But in the question, they use it as I note.
Sorry.
They
Yeah,
use it
because
as.
that's like if you introduce the signal, a signal would be rippling over that ICQ, which is basically it's like if there was any such thing as biasing current, that would be it. It's the no signal collector current.
Okay.
So if you don't put in coupling, that is the signal that will go to the load. That's why we put in a coupling like things like transformers and capacitors to stop that signal from going into the load. Yeah.
Okay. I hear you. Daniel is saying it is IC when no signal is applied to the amp. Okay, okay. Doesn't it just mean DC, Fiona? Okay. So okay. Yeah. So we're saying I naught max. I wrote it here. I naught max squared is Z1. I'm still not sure why you're using Z1, but we're using Z1. So we had 100 milliamperes. So 0.1 over root 2, because you're using RMS, times Z1 yetu tumepata as 49. So I was able to use this is squared. This should be squared. I was able to do up to here. I wasn't so sure what I should use as my power input at this point. So, because efficiency, I've gotten my power output, but I need to get power output over power input in DC times 100. I don't know who knows how we'd use power input. Yeah, would use VCC, ICQ. So those are things that I was still to look at yet. So Fiona, we are saying that it is the IC when no signal is applied, when no signal is applied to the amplifier. So if there's no AC signal that has been applied to the amplifier, it's simply DC. So yeah. So someone will be able to get efficiency, not necessarily now, but yeah, I've gotten power output. I don't know what to use as power input. That was where my problem was with this one. Yeah. Hello.
Celestine, you've mentioned you got power output, right?
Mm-hmm.
Okay.
Yeah, at least that is how we did it in class. Yeah.
Something doesn't add up here.
So I think,
Celestine, think about it this way.
and that is what I also.
I'm
Mm-hmm.
thinking about it this way. Usually, when we're calculating the power input, we don't normally factor in the signal, right? We just say that power input is the power that was supplied by VCC, and then power output is when you add in now the part of the signal that's been amplified, when you add it to the VCC, that is what makes it an output. So how is it, Ebu, back to your power output, just the expression for power output. Right, output max. Yeah, that this concept did take a while to sink, and it's starting to lose weight. It's
So
yeah, nilikuwa nimegrasp but kinaanza kuni starting to play mind games on me. I'll get back on it.
So I was thinking we leave this as an open thing. Kila mtu aende afikirie how we could solve this question, yeah. So that tusishinde hapa, ikileta shida pia we'll just ask the lec, because at least now we have a platform. Yeah.
The last
Yes.
Fiona is asking if you can just use the formula for PDQ that we saw earlier, where it's VCQ multiplied by ICQ, because if we stick with the logic that the zero signal collector current is a DC current. That means that it won't have an RMS value because it's DC.
Okay, net. I think I tried to use.
So won't it just be like I squared R?
Okay, I'd have to do that again. I'd have to do that again to be able to confirm that. So I think we should put a star on it and we all go and look at it. Yeah. And then yeah, we see what we come up. When are we meeting? I don't know kama ni kesho ama ni sato. We see what we'll have come up with by then. If someone has a
Saturday
solution, you
sounds
can
good.
post tomorrow in the group. Okay. So
Gishero, how does Saturday sound?
The suggestion was raised in the group, I think, yesterday.
Nilisikia ilikuwa ikuwe
No,
Thursday.
it's
Rwanda was raised Thursday and Saturday. I feel like Sunday would be cutting it too close. So yeah, so we have it sent over to the group as well to decide on how do we play out this one. Gishero.
you should stop the recording.
Oh yeah, Gishero.
We're done.
Hizo ni bundles muhimu sana.
So let's tumemaliza.
No, I was just saying you can stop the recording.
Yes, now I'm asking if you're done presenting, like, is that all for today?
I think she is.
Sorry?